Hello everyone, welcome back to another Geostats lecture video. And in this lecture video, I want to continue our discussion talking about spatial autocorrelation by talking about a critical component of pretty much every measure that we have of spatial autocorrelation. And that's this idea of a weights matrix. Or sometimes you'll hear it referred to as a neighborhood matrix. Or a connectivity matrix. Oops, not com. Right. Weights matrix, neighborhood matrix, or connectivity matrix. And basically what these do is they are an organized way of measuring adjacency. And so the basic structure is you have the object ID or object number going along the top, and then you have the object number going along the side. Right? And so you can imagine this forms a grid. Right? And inside of this grid cell is a measure of whether or not the object is adjacent or not adjacent. So it gets a 1 if adjacent, and a 0 if not. Right, so it's a 1 or a 0. Now, the tricky part to these matrices is determining what do we actually call adjacency. How do we define adjacency? Okay, so what I want to do is I want to go through an example of setting up a weights matrix given 9 objects. Right. So in this example, right, here's our objects down here. This is going to be our weights matrix. Let's go ahead and actually label that. Ooh. Right, this is going to be our weights matrix. It's going to be our weights matrix. So this is our data set. Right, so you can see we have 9 polygons labeled 1 through 9. That corresponds to the numbers in the first row and first column here. First column, first row. Right, so this 1 refers to this 1. This 2 refers to this 2. So basically what we're going to do is we're going to go through each object pairing and we're going to say, is the object in the row adjacent to the object in the column? So for example, this first box right here is saying, is object 1 adjacent to object 1? Well, by default, we're going to say yes, it is, because you are adjacent to yourself. Okay. So before we go any farther, I want to talk about this idea of adjacency. Right, and there's really multiple options. The first one would be to, let's consider these 4 here. I think we can all agree that 1 and 2 are adjacent. And we can all agree that 1 and 4 are adjacent, right? Because they share an edge. Right? That's the first type of adjacency, is they share an edge. The second type of adjacency is, what about 1 and 5? Right? Are 1 and 5 adjacent? Well, maybe, right? Do you count sharing a vertice or a corner? Do you count that as being adjacent? If you do, which you certainly can, that means something entirely different than just calling on edges, right? So share a vertice or a vertex. And finally, would you consider 1 and 3 to be adjacent? Probably not, but there are circumstances where you might actually want to consider 1 and 3 to be adjacent, and we call that a lagged adjacency. Adjacency, right? A lagged adjacency. Primarily, we're going to be talking about these first two, where they share an edge and they share a vertex. Lagged adjacency is definitely important, and it's something to keep in mind. We're not going to talk about it too much now. But if we only consider objects that share an edge, there's a special name for this. This is called Rook adjacency. It's called Rook adjacency. You can think of this like the chess piece, right? The rook from the chess can only move up and down, left and right, right? In this case, right, the only things that are adjacent are either up and down or left and right. Similarly, if they share a vertex, we can call this queen, right? Let me just see if I can clean that up just a little bit. We can call this queen adjacency, right? Where they share vertex. So for right now, what I want to do is I want to fill out this weights matrix using the Rook's case. Make that look a little less sloppy. Let's use the Rook's case for this adjacency, right? Which again means we're only going to consider them adjacent if they share an edge. So we already said by default you're adjacent to yourself. So we can go ahead and throw ones in on the diagonal because everything is adjacent to itself. We're going to fill in this top half here because the bottom half is going to be the same, or I should say reflection, the bottom reflection. We're going to fill in this part up here. So let's look at 1 and 2. Are 1 and 2 adjacent? Well, they share an edge. So yes, they are. So in this case, this would get a 1 because 1 and 2 are adjacent. What about 1 and 3? Well, we're not dealing with lagged adjacency, so this is going to get a 0. They are not adjacent, right? There's no scenario where 1 is adjacent to 3 under our Rook adjacency rules. What about 4 and 1? Well, 4 and 1 definitely do share an edge, right? We've kind of already talked about this a little bit, right? They share this edge right here, so they would get a 1 as well. What about 1 and 5? Well, 1 and 5, right? They share this vertice right here. They share this vertice right here. They don't share an edge. So under the Rook adjacency rules that we're working with, those would actually get, this would also get a 0. Ooh. This would also get a 0, right? Even though they share a vertice, because we're dealing with the Rook's case, right, they do not share an edge. What about 1 and 6? Nope. 1 and 7? No. 1 and 8? No. 1 and 9? No. Well, what about 3 and 2? Do 3 and 2 share adjacency? Yes, they do. So this would get a 1. What about 2 and 4? Again, right, we have this, they share a vertice, but not an edge. And based on our Rook's case, they would get a 0. 2 and 5, right? 2 and 5 do, right? They share this edge right here. So that would get a 1. 2 and 6, again, same thing. They would be the queen's case, so they do not in this scenario. 7 and 2 do not. 8 and 2 do not. And 9 and 2 do not. What about 4 and 3? They do not. If I'm going too fast, pause the video. Once we get the matrix filled out, pause the video, go back in, or pause the video now and try and fill in the matrix yourself. I'm going to go through a little quicker just to kind of speed things up a little bit. All right, so 5 and 3, they would be the Rook, the queen's case, but not in the Rook's case. 6 and 3 share an edge. 7 and 3 do not. 8 and 3 do not. 9 and 3 do not. 5 and 4 do. 5 and 4 do. 6 and 4 do not. 7 and 4 do. 8 and 4 would in the queen's case, but they do not in this case. And 9 and 4 do not. What about 5? So 5 has borders with 6. 7 would be the queens. 8 and 9 would be the queens. 6 borders 7. It does not. 8, it would in the queen's case. And 9, it does. Does 7 and 8 border? Yes, they do. Do 7 and 9 border? No, they do not. And 9 and 8 do. Right? So this right here, if you imagine mirroring that down here, this would be our weights matrix. Again, just a measure of how things are connected. You get a 1 if you're adjacent, and you get a 0 if you're not. And we can define adjacency with Rook adjacency if they have to share an edge, if they can only share an edge. We get Queen's adjacency if we included just a vertex. And then again, you can get something called lagged adjacency, where you count multiple objects away. Hopefully this made sense. I know this was a lot of just sort of counting adjacencies, but this weights matrix is the fundamental piece of pretty much every single measure of spatial autocorrelation that we're going to work with. So understanding how we got from our polygon setup here to our weights matrix here, right? Going from this to this is going to be very, very important that you understand conceptually what that means. So that when you see something like Wij, which we're going to be seeing a lot of, you'll understand that we're talking about a weights matrix and whether or not they're adjacent or not. So hopefully that makes sense. And as always, please reach out. Thank you.